Hello and welcome to our lesson on solving rational equations with applications. And the rational equations that we're going to look at today are what we call proportions. Okay, now let me just back up a little bit before we talk about proportions in general. What does it mean for an equation to be a rational equation? So just like the rational expressions that we were dealing with for most of this module, a rational equation contains fractions of polynomials. So we're looking at fractions, not just fractions, but fractions of polynomials. And if it's a rational equation, then those fractions of polynomials are going to be separated by an equal sign. So you could see these fractions of polynomials before and or after the equal sign. So the equal sign makes it an equation. The fractions of polynomials make it rational. Now, technically, rational equations have restrictions. Okay, we know. Well, rational expressions have restrictions too. Fractions in general have restrictions. There are certain values of x that we cannot accept because those certain values of x make the denominator of the fraction equal to 0, and 0 in the denominator of fraction isn't defined. So values of x that make the denominator equal 0, that make our denominator equal 0, they have to be restricted. Okay, they have to be excluded as possible x values, which means for an equation they have to be restricted as possible solutions. So for example, in this first equation, there's no restriction on the numerator, so I'm not concerned about the numerator when I'm looking for restrictions, but in this particular denominator, x plus 1, if I said that x was equal to -1, well, that -1 here and +1 would put a 0 in the bottom of the fraction, which is no good. So looking at this equation, I would say there are two restricted values, which I'm going to abbreviate RV. We would say that x could not equal a -1 because a -1 would cancel that +1 and make a 0 in the first fraction. And then in the second one, +5 would do the same thing. So x could not equal -1, and it could also not equal a +5. Okay? Looking at the second equation here, if I put a 0 in for x here, then 3 times 0 would make a 0 in the bottom of that fraction. So if I was looking for restricted values for this second equation, I would say x cannot equal 0. And then if I put a +4 in here, 4 minus 4 would make a 0 in the bottom of that fraction. So x could not equal 0, and it could not equal 4. Okay? So we have to exclude x values that make our denominators equal 0. Now this doesn't happen often, but a small percentage of the time when we solve a rational equation, we end up with one of those restrictions as a solution. If that happens, we call it an extraneous solution. So an extraneous solution is a solution that is restricted. Okay, now if that happens, that extraneous solution isn't considered a valid solution. It is not a valid solution to the equation because it causes the denominator of the fraction to equal 0. So even though we're going to call it an extraneous solution, it isn't considered a solution. Okay, so it's possible we solve a rational equation and we get one solution that happens to be extraneous. In that case, there would be no valid solution for that equation at all. That equation would have no solution. We might see some cases where we get two solutions. One of them is extraneous, but one of them isn't. If that were to happen, then we would just accept the one valid solution and not the extraneous. Okay, so we're going to see more of that, but we have to look for those restrictions. Okay, now there are two types of rational equations that we're going to solve. We're going to focus on one of those in this topic, and those are proportions. So a proportion is the easier of the two types to solve. A proportion is when you have an equation with exactly one fraction on either side of the equal sign. So one fraction equal to one fraction. So if you have exactly one fraction on either side of the equal sign, then those fractions are proportional. And proportions are nice. So these are three examples of proportions. And if you look at the first one, for example, we know that 4/6 is going to reduce to 2/3, so I know those two fractions are equal. But another feature of proportions that's nice is the cross products. If I was to cross multiply here, I get 4 times 3, which is 12. If I was to cross multiply on the other side, 2 times 6, I get 12 again. Those cross products are equal, and that's not coincidental. If we have a proportion, those cross products will always be equal. So here again, for example, 5 times 2 is 10, 1 times 10 is 10. Those cross products are equal. Or 9 times 6 is 144, and 2 times 72 is 144. Those cross products are equal. The cross products being equal tells me that those two fractions are proportional, or that they reduce down to the same thing, or vice versa. If I have two fractions that reduce to the same thing, or they're proportional, then those cross products have to be equal. Alright, so the cross products of proportions must be equal, which is really helpful if we're trying to solve a rational equation. All right, if we have a rational equation that is a proportion, then we're going to cross multiply and our fractions will go away. So before we solve, we still want to look for our restrictions. We're going to look for restricted values of x, and then if we have a proportion, we're just going to cross multiply. Once we cross multiply, our equation will no longer contain fractions, and then we should be able to solve the resulting equation. So it could be linear, looking for one solution. It could be quadratic, looking for two. But we're going to solve whatever is left after we cross multiply. Okay? So for example, on this first one, before I solve, there's a restriction here. X can't be 0 because it would create a 0 in the bottom of that fraction. No restriction there because there's no x in the denominator of that fraction. So just to kind of keep on the back burner here, I have in this number 1 that x cannot equal 0. That's my restricted value. Okay? And now if I cross multiply, here I'm going to be multiplying 4 times 6x. And then if I multiply here, I'm going to have to distribute 9 to the x minus 1. And because this is a proportion, those cross products have to be equal. And so we are left with, 24x on this side equal to 9x minus 9 on the other side. And now I'm going to get my x's together. So let me subtract these 9 over. And 24 minus 9 is going to leave me 15 x's on this side, and then I still have the negative 9 here, and then it's one more step to solve. If I divide by 15 on both sides, then x is all by itself equal to, now negative 9 doesn't divide by 15, but that does reduce, so we're going to make our reduced fraction negative 3 over 5 our answer. And that is not restricted. The restriction was 0, which means that's going to be a valid solution for us. Okay. Now, if you really wanted to check your work, you could use your calculator to do that. So if I make a fraction here, on the top of the fraction, I'm saying that negative 3/5 minus 1, and then on the bottom, 6 times the negative 3/5. That value should be equal to 4/9. And I could see that both of those are the exact same 0.4 repeating decimal value, so I've confirmed that is my solution. Okay? So let's try this again. We have a proportion number 2, one fraction equal to one fraction, which means their cross products are equal. Before I solve, though, I do have a restricted value. In this one, x cannot be 3, because a 3 minus 3 would make a 0 in the bottom of that fraction. So I know what x can't be. Let's cross multiply and figure out what it can be. So here, excuse me, 3 is going to have to distribute to x plus 3. And then here, 5 is going to have to distribute to x minus 3, and again, those cross products will be equal. So that's going to give us 3x plus 9, and that has to equal 5x minus 15. And now let's get our like terms together. I'm going to subtract these 3 x's over, and that's going to leave me with 9 equal to 2x minus 15. I'm going to add that 15 over. That leaves me with 2x equal to 24. And then in one last step, I can divide by 2. And now x is all by itself equal to 12, which is not restricted, which means 12 is going to be my valid solution. And again, if I wanted to check that, Then I could plug it in, so I should have a fraction with 12 plus 3 in the top, 12 minus 3 in the bottom, and that fraction should be equal to 5/3. Hello, sorry, 5/3, and so I get 1.6 repeating on both of those. So again, confirmation that 12 is in fact my valid solution. Okay, not too bad of a process. If you want and you're feeling comfortable, then pause the video and give it a try. Now before we solve this one, we have two restricted values. X cannot equal a positive 4 because it would make a 0 there, or a negative 1 because it would make a 0 there. So we can't be 4 or negative 1. Again, we know what it can't be. Let's go ahead and cross multiply and find out what it can be. So 5 has to distribute to x minus 4, and 3 has to distribute to x plus 1, and again, those cross products have to be equal. So we're looking at 5x minus 20 on one side, and 3x plus 3 on the other. Let's get our like terms together. So let me subtract these three x's over. That's going to give me 2x minus 20 equal to 3. I'm going to now get x by itself. So if I add 20, then I have 2x equal to 23. And then one last step. Let's divide both sides by 2. That doesn't divide or reduce, so we're going to have a fraction of 23/2 as our solution, our one valid solution, because that solution is not restricted. Okay? And I squished that in there. I didn't really have to because I have more space. Let me just write that again. So we have 23/2. And there it is. Again, if you wanted to use your calculator to verify that solution, it's going to work. The only time we really have to worry is when the solution occurs as a restriction. Okay, so far. And we're going to be looking at more rational equations in the next topic, so I know we didn't get a restriction here, but it's going to happen, I promise. All right, so I think proportions, again, easier type of rational equations to solve. In the next topic, you're going to see some that are a little more challenging. But let's up it up a little bit here. So we're going to look at some applications of proportions, which just means we're going to apply the process, the solving process, to some word problems, which can be a little challenging because there isn't, one set way to set up your equation and solve every time. But in general, when you're solving a word problem, make sure that you're reading the problem first so you understand what it's giving you and what it's asking for. And if you want to mark the text along the way, highlight important information, underlined, list stuff out, whatever is going to be helpful for you. And whatever the problem is asking you to find is going to help you define your variable in the situation. And, you want to try to, if it's possible, to organize the information. So if it's helpful to write stuff out in words, or again, to make a list or a picture to go with your situation, try to organize somehow. And the hard part is using all of the information that you're given, using the variable that you've defined to write an equation that models your scenario. All right, that's obviously the important step there. Once we have it, and these few examples are going to be proportions, we're going to solve by cross-multiplying. And just make sure that in the end we have an answer that makes sense, and make sure you're answering the question with an answer that makes sense. Okay? So these examples, again, these are going to be proportions, so we're going to be dealing with some proportional amounts. So looking at number 3, which... okay, good. I can number a paper. I was like, this is the fourth problem, but one's called a U-try. Number 3 says the ratio of math majors to business majors at ASU is 1 to 5, respectively. So that means for every one math major, we're looking at 5 business majors. So 1 to 5 math to business, or 5 to 1 business to math. And it says there are 21,000 students enrolled in the 2 departments. So this is 21,000 students total. And it's asking how many students are math majors. How many math majors are there total? That's what we're looking for. That's going to be our variable. I'm going to call it x. Okay, so what we're looking at are, again, proportional amounts. We're looking at math majors to business majors. So whenever it's a proportional amount, I like to start by just writing out the words for the items in the proportion. So in this case, again, it's math and business majors. And if you switch that, put business in the top, math on the bottom, that's totally fine as long as you're consistent. Okay? So what we have first is given that there is one math major for every 5 business majors. Okay, one math major to every 5 business majors. So there's one of our fractions. And then the second one says, how many math majors are there total? We don't know. We're going to call that x, to how many business majors are there total. So the 1 to 5 is the reduced fraction, and the other fraction is the total, right? How many math majors are there out of the business, and how many business majors are there total? So you might be tempted to put 21,000 here, but we have to be careful because 21,000 is all of the students. It's not just the business majors. So what do we put in the bottom of the second fraction is the only challenging piece to this problem. So let's just pretend, there were 1,000 business or math majors, or not 10,000, 1,000. If there were 21,000 students total, the other 20,000 would have to go here, right? If there were 2,000 here, then the remaining 19,000 would go on the bottom. If there were 3,000 math majors, then the other 18,000 would go on the bottom. So if there are X amount of math majors, we have to subtract them from the 21,000 to figure out how many are left for business majors. So on the bottom of the fraction, it's the 21,000 students total minus the math majors. The rest would be the business majors. Okay, and now we have our proportion, so we can cross multiply. And let me just give myself a little more space. So when we cross multiply, the 5 is going to be multiplied by x, and the 1 is going to multiply by 21,000 minus x. Again, those cross products will be equal. So we're looking at, let's see, 5x equal to multiplying by 1 doesn't change either of these terms. So let me get the x's together. If I add this one over, we're looking at 6x equal to 21,000, and then we're going to divide both sides by 6. So if I have 6x equal to 21,000, again dividing by 6, I should come up with my answer. And 21,000 divided by 6 is going to leave me with 3,500. So if this was out of context, we would just box that in as our answer, but that 3,500 represents the math majors. That's what we called x. So we have 3,500 math majors. Does that seem like a reasonable answer? Well, let's just check. If we had 3,500 math majors, okay, if I wanted to just do a quick check here, if I had 3,500 math majors, then 21,000 minus the 3,500, the 21,000 students total in those two departments, minus the 3,500 math majors, would leave me 17,500 business majors, and that fraction should reduce to 1/5. And if I did 3,500, my gosh, over 17,500, do we get a fraction that reduces to 1/5? We do. Okay, so we can just do a quick check of our work to make sure that it's reasonable. And that wasn't so terrible. Okay, number 4. Let's see. A basketball player has made 21 out of 30 of his free throws this season for an average of 70%. So 21 out of 30 is 70%. So we got to be careful here. They're giving us the same information twice. Okay, so 21 out of 30 is 70%. Same thing. I'm just going to cross one of them off just so that it doesn't confuse us. Okay, I don't want to use the same information twice. So then it says, how many consecutive free throws must be made to raise his average to an 82%? So how many consecutive free throws are we going to make? Must be made. That is our variable here. Let's call that x. And he's trying to raise his average to an 82%. So the 21 out of 30, I think, well, hopefully it's clear that's going to be the first fraction there. And the 21 out of 30 is how many free throws he has made out of how many free throws he has attempted. So let's go with the makes versus the attempts. Again, I'd like to put the words out here first so I can try to organize, okay? So right now he's got 21 out of 30. Now it says, that's a 70% average. It says how many consecutive free throws is he going to make in order to raise his average to an 82? So he wants to add to the number of free throws he makes, and he wants that to, instead of being a 70% average, he wants it to be an 82% average. And 82% is 82 out of 100. So he wants to raise it to an 82 out of 100. Now, we're obviously going to be adding consecutive free throws to the amount of free throws that he makes, but if he's making those free throws, he's also attempting them, and if they're consecutive, one after another after another, he's adding the same amount to the makes and the attempts. So for example, if he was at 21 out of 30 and he made the next shot, then he'd be 22 out of 31. And if he made the next shot, he'd be 23 out of 32. He's going to be adding to the makes and to the attempts the same amount every single time. Okay, so now we have our equation. So these are proportional. We're going to cross multiply. So the 82 is going to have to distribute to 30 plus x, and the 100 is going to have to distribute to 21 plus x, and those have to be equal. Okay, so 82 times 30 is 2,460. Let's not do anything stupid here. Let's see, 82 times 30, 2,460, plus 82x equal to, I could do that one, 2,100 plus 100x. And I need to get these x's together. Let me subtract these 82 over. So now we're going to go here, we're going to say, let's see, 2,460 left equal to 2,100, and 100 minus 82 is going to leave me 18 x's. Subtract over the 2,100, and so now we're looking at 360 equal to 18x, and now I can divide over the 18, and that leaves me with x equal to 20. So apparently, if he makes the next 20 free throws that he attempts, he will raise his average to an 82%. So we want to answer this as 20 consecutive, and that's not going to fit. 20 consecutive free throws. That's how many he's going to have to make. The next 20 free throws that he takes, he's going to have to make if he wants to raise his average to an 82. And again, we could check that if I wanted to do a quick check. So if he made the next 20, he had 21 made. If he added 20 to that, then he would have 41 made. And if he had originally attempted 30, but he attempted the next 20, then that would be 50. So 41 out of 50 is, in fact, an 82%. Okay? So if you wanted to check, just make sure you've got a reasonable answer. Always a good idea. Okay, so I don't know what I just deleted. No idea. Let's look at this last one. And again, if you're feeling pretty good about this and you want to try it, I think this last one's pretty manageable. So feel free to pause. It says that the scale drawing on a blueprint shows that a 10-foot wall is 2.5 centimeters long. If you were to draw in a 12-foot wall, how many centimeters would it need to be? So we are looking at a scale drawing on a blueprint, and it's converting a measurement in feet to a measurement in centimeters. So we're going to be looking at proportional amounts of feet and centimeters. And again, if you flip that, it doesn't matter as long as you're consistent every time. So the first thing that we know here is that a 10-foot wall is 2.5 centimeters on this drawing. It says if you were to draw in a 12-foot wall, how many centimeters would it be? We don't know, let's call it x. So a 12-foot wall, I'm going to put that on top because that's feet again, is how many centimeters? So 10 feet is 2.5 centimeters, 12 feet is how many centimeters? Again, I think that's pretty straightforward. Let's cross multiply. So 12 times 2.5 is going to be 30. I believe 12 times 2.5, not 25, 2.5. Okay, yeah, 30. So 12 times 2.5, oh, I just want to make sure I show my work. 10 times x, those are going to be equal. So if 30 is equal to 10x, let me go back to blue. OCD people. Okay, if 10x is equal to 30, then when I divide over the 10, I see that x has to equal 3. So if x equals 3, that means that that 12-foot wall is going to be 3 centimeters. So 3 centimeters for that 12-foot wall. Okay, not so bad. And in the next topic, we're going to look at rational equations again. We will probably see some proportions in the next one. But the setup won't always necessarily be a proportion for what we're going to look at. You'll see. And we will come back to the restricted values, but hopefully you've got enough to go on this particular assignment. So go ahead and practice that one out, and if you are running into trouble, need some extra help, then just reach out. All right, guys, take care.